Hey everyone, today we'll be discussing uncertainty estimation in deep neural networks.
Deep learning models are used in a wide variety of applications for their impressive performance. However, quantifying uncertainty in these models is still a largely unsolved problem. In this paper, we implement various methods for estimating aleatoric, epistemic, and approximation uncertainty in deep neural networks. For aleatoric uncertainty, Monte Carlo dropout and deep ensembles are computed on the MNIST dataset. For epistemic uncertainty, orthonormal certificates are computed on the Boston housing dataset. For approximation uncertainty, we generate our own data from the cubic function with predefined noise and show the resulting uncertainty after training using different degree models. These methods are then assessed and analyzed for their prediction accuracies and uncertainty estimates.
To estimate aleatoric uncertainty, which is uncertainty based on the variance of our data, we utilize two main methods, Monte Carlo dropout and deep ensembles. Monte Carlo dropout estimates uncertainty by applying dropout at test time, and deep ensembles computes a weighted average of predictions over many deep learning models. We first examined Monte Carlo dropout and uncertainty by conducting a simple experiment. We trained a model on the MNIST dataset and fed in new data points. We rotated the image 1 and fed it into our Monte Carlo dropout model. Monte Carlo dropout produces a wide range of values for the images that are rotated, which increases the variance for the prediction of an image and therefore the uncertainty. This is what we want to see, as these rotated images aren't any true number. The next experiment we conducted was producing a randomized image and feeding that into the Monte Carlo dropout model, and the deep ensemble model, and a normal neural net. Since this is a bad data point, we should expect that the model would be highly uncertain about the point. A normal neural net produces a prediction of 8, however, with high confidence. In contrast, the ensemble classifier and a Monte Carlo dropout model effectively reduce overconfidence in this prediction, reducing our highest probability by a factor of roughly 2.
We measured epistemic uncertainty using orthonormal certificates, a procedure formalized in 2018. Epistemic uncertainty is also called knowledge uncertainty and stems from a lack of training data in parts of the feature space. As you might expect, it is difficult to make accurate predictions for an input when we don't have comparable data points. Orthonormal certificates are used to identify exactly that, outliers that are very different from our training data, for which we can't generate very confident predictions. First, we wanted to show that there's value in separating outliers from in-domain values, that we really should be less confident when making predictions about outliers. To do so, we used k-means clustering to identify outliers in the Boston housing dataset, and then trained a neural network to predict housing prices. Unsurprisingly, we found that our model performs much worse on outliers than on in-domain samples, with a mean squared error of 148 relative to roughly 25 on in-domain samples. Hopefully, this difference in performance is a convincing indicator that there is value in separating in-domain and out-of-domain data. Next, we trained orthonormal certificates to classify new inputs as either in-domain or out-of-domain. In the plot on the top right, you can see that our procedure gave out-of-domain samples, highlighted in red, much higher uncertainty scores than their green in-domain counterparts. Our ROC-AUC of 0.86 further supports that orthonormal certificates are an effective way to identify inputs with high epistemic uncertainty.
Finally, we show approximation uncertainty, or the errors made by simplistic models unable to fit complex data. While this is uncommon in deep neural networks, we note its presence for the sake of completion. To do this, we create a model in which we are certain that the ground truth data it is generated from is a known distribution, which in our case is a cubic function with 100 points lying between -5 and 5 as shown in the figure on the left. Noise is then added to this data with a standard deviation of 10 and is split into training and test sets. Then the model is trained using different degrees of classifiers, and the resulting validation MSE scores across an increasing number of training samples is shown in the figure on the right. The gap between the best performance of the linear and quadratic classifiers and the cubic classifier is the approximation error. And that concludes the summary of our paper. We thank you for your attention.